So in multiplying these through together, remember, multiply everything in the first parenthesis by everything in the second parenthesis. So that in that first one, x is going to multiply by x and the negative 3, and the 8 is going to multiply by x and by the negative 3 as well. So when we do that multiplication, the x times x gives us x squared. Then we do x times negative 3, that will give me minus 3x. Then 8 times the x, so that is plus 8x. And then 8 times negative 3 gives us a negative 24, or minus 24. Then, seeing what we have there, can we simplify this at all? Yes, that can simplify a little bit. Notice we do have two like terms, the x's. The x squared we can't touch, but the x's we can. So the x squared, there's nothing else squared, so that's why it stays the same. And then we have negative 3x plus 8x. That gives us plus 5x. And then the minus 24 stays the same, so that's what we're looking at for number 1. All right, on number 2, 2x times x gives us 2x squared. 2x times a minus 5 gives us minus 10x. 1 times x gives us just 1x, or x. And then 1 times the negative 5 gives us a minus 5 there. And then, again, combine the like terms. The 2x squared stays 2x squared because there's nothing else that has an x squared in it. But I can do the minus 10x plus x. That's going to give us minus 9x. And then the minus 5 hanging on the end. Number 3. It's not going to give us 9x squared plus or minus 25 because we cannot simply distribute an exponent. Squaring something means multiplying it by itself. So the very first thing we have to do on this one is rewrite our problem as 3x minus 5 times 3x minus 5. And then we're going to multiply that out. And so when we do that, we're going to end up with 3x times 3x, which is 9x squared. 3x times minus 5 is minus 15x. Minus 5 times 3x is another minus 15x. And then negative 5 times negative 5 is a positive 25. And then once again, yes, we do need to combine the like terms. So our final answer here ends up being 9x squared minus 30x plus 25. And then finally for number 4, it's going to be a very similar kind of thing here in number 4. All right, so for number 4, I want to start by writing that x plus 4 squared out the long way. So this is going to be 3 times x plus 4 times x plus 4. Notice the 3 is not squared, so the 3 still only appears the once. Then, you have a choice about what you do next. Some people will multiply the 3 in. If you do that, it only multiplies into one set of parentheses because it only appears once. Or you can multiply the two parentheses together and then deal with the 3 after that. I find the latter option to be the easier, so that's what I'm going to do. I'm not going to touch the 3 yet, but I am going to multiply x plus 4 times x plus 4. But again, either way works. When we do that, that gives us x squared plus 4x plus 4x plus 16, which simplifies down to be x squared plus 8x plus 16. And then I can go ahead and deal with 3. The 3 needs to be distributed to every term. So I'm going to multiply all of those by 3, which gives me 3x squared plus 24x plus 48. And then that's our final answer for that one because now all the parentheses are gone, so we've multiplied everything in, and there's nothing else I can combine, no other like terms. So factoring these is basically doing what we were just doing with expanding, except backwards. We're going to be creating the parentheses. A quick reminder about how to do these. I'm looking and seeing what two numbers add to the middle number and multiply to the last number. So like in the case of number 1, what adds to 5 and multiplies to 6? Well, that'd be 2 and 3. And so then our answers are going to be x plus 2 times x plus 3. Or you could also have written it as x plus 3 times x plus 2. That order does not matter. And then use that to help you remember on how to do the other 3 as well. So keep going with them. All right, now let's take a look at the rest of these. In number 2, again, what two numbers add to a negative 8 but multiply to negative 9? Sometimes this can be tricky because we tend to have a little bit of a blind spot with it. It's the 1 option. So it's actually negative 9 and a positive 1. And again, the order doesn't matter. You could have also written it as x plus 1 times x minus 9. Just make sure that this correct sign goes with the correct number. So the minus has to be with the 9. And the plus has to be with the 1. All right, number 3, we do the same thing. We figure out what adds to negative 16, multiplies to 64. And we end up with x minus 8 times x minus 8. But I do not want to leave my answer looking like that. X minus 8 times x minus 8 is a little bit sloppy. We need to refine it a little bit. A shorter way to write x minus 8 times itself is to write it as x minus 8 squared. So that's the way I want to write that answer, is x minus 8 squared. And then for number 4 is a little bit trickier. We haven't necessarily had to deal with one like this before, but number 4 from the previous set can give you a little bit of a hint. Notice I can divide all 3 of those terms by 2. So that's actually the very first thing I'm going to do. So if I divide all of those by 2, I end up with x squared plus 10x minus 24. Now, I still need this to be equivalent to the same thing though. So I'm going to put parentheses around that and show that it would be equal if I multiplied everything through by the 2. Basically, we've done distributive property backwards here. We factored out a 2 first. Now we can factor the quadratic by doing our normal add to, multiply to. It's a matter of what adds 10 and multiplies to negative 24. And so for this one, the 2 stays out front. Our two numbers are going to be 12 and negative 2. So it's x plus 12 and x minus 2. So we're going to start with our new graphing today by looking at this old graph. So we're here looking at absolute value of x minus 6 minus 8. So the absolute value, remember, that tells us it's going to be a V-shaped graph. The minus 6 moves it to the right 6. The minus 8, because hanging on the end, that moves it down 8. You should end up with a graph that looks like this. Check it, make sure that you're on the right track with it. Now a little bit of extra review. What's the range of that graph? Remember, the range is a description of possible y values. Yes.
Y is greater than or equal to negative 8.
Excellent. Yep, our range is y is greater than or equal to negative 8. Because that range is describing the graph. It's saying that this graph includes all of the y values that are at negative 8 and above. So it's including all of those y values. Now today we're going to be adding on the graph of x squared, the quadratic graph. And then we're going to be comparing this to the graph that you just made. So when we're making a new graph for the very first time, usually I like to start by making a table of values. And so that's what we're going to do here, is we're going to make a little table and then we're going to plot those points to see what our graph of x squared looks like. A great number to start with when doing this is just a simple x value of 0. If x is 0, what is y? That's basically saying, what's 0 squared? 0 squared is 0. Because that means we're doing 0 times 0, and 0 times anything is going to be 0.
Okay, that would be the exponent of 0 to make it 1.
All right, then let's go to x being 1. What if x is 1? What's 1 squared? 1, because 1 times 1 is 1. Okay, if x is 2, what's 2 squared? 4. Notice there is our first difference from the absolute value graph that we had done before. The first couple points looked the same, but this one now is different. What if x is 3? Well, 3 squared is 9, yes. Okay, and what if x is 4? That gives us 16. I'm actually not going to worry about anything past that at the moment. Now, of course, our table does exist for far more points than that. There's an infinite number of points we could put in. But if I start plotting these points that we've put in so far, I actually don't even have enough room for the 416. on my graphing grid. So I'm just not going to worry about any of the points past that, but just know that if you wanted to, you could continue it on to like 525, 636, and so on, if your graphing grid allows it. All right, so we've seen what happens with 0 and up, but what about in the negatives? What if x is -1? What is -1 squared? It is +1, yes. Because a negative times a negative is a positive, so -1 squared is -1 times -1, so it's got to be +1, yeah. Okay, let's do -2 now. What's -2 squared? 4. -3, 9. -4, 16. We're just squaring each of those numbers. And notice every time you square a number, you always get a positive out. And so there we can actually see the points that we end up plotting and actually fitting on for this one. Draw the curve in through those points, and this is what you should be looking at. Notice it's a nice curve. None of it is straight. Not one piece of this graph is straight. It's all a curve. It's especially a curve over here around 0, because here at 0, it technically is actually leveling out. If we were to zoom way in on that point, we would see that the graph actually ends up looking like it's flat right at 0. It's just, you got to zoom in really close for it to start looking that way. But it does flatten out as you hit that point. And then if we can graph x squared, then we can give the range of x squared. So what is the range of this graph? Okay, I heard greater than 0. So greater than or equal to 0. And what is greater than or equal to 0 here? The y. So that is our range. Because again, the range is a description of the graph. The y values are included in it. So we're saying, okay, we're starting at 0, and then we're going up from there for our range. Okay. Now the fun begins. We are now going to graph y equals x minus 6 squared minus 8. We actually are going to approach graphing this the same way that we graphed that absolute value one earlier. The minus 6, that's inside with the x. It follows the same rules as they did with the absolute value. This minus 6 is going to move our entire graph to the right 6 units. The minus 8 hanging on the end, it's going to do the same thing. It is going to move everything down 8 units. So normally, our first point is here at 0, 0. But in this case, it's moved right 6 and down 8. So it is instead going to be starting at 6, -8. Seem kind of familiar?
Yeah.
I hope so at least, because that's the same thing you did with the absolute value graph we did a minute ago. From here, use that table, and you'll actually get to know that table so quickly that you'll just be able to do it off the top of your head, to fill in the points. So like if I go over 1, what is 1 squared? 1. So that means if I go over 1, I go up 1. And remember our graph did this exact same thing on both sides? So it does the same thing on both sides of that point. Okay, what if I go over 2 from that starting point? What's 2 squared? 4. So from that starting point, we go over 2 and up 4. What if I go over 3? How far up will I go?
Yeah, you went over one. Oh, from there.
So all of these counting overs and ups, they're relative to that starting point. By the way, what do we call that starting point? Vertex, absolutely. So it's all relative to the vertex and where we start. All right, so then I went over 2 and up 4. Let's go over 3. What's 3 squared? 9. Okay, what if we go over 4? What's 4 squared?
16.
Getting the idea, right? And so then you plot those points, draw in the curve. This is what you should be looking at now for your graph. Now, I want to compare that graph that we just made to that absolute value graph that you made earlier. So what are some similarities and differences that we see between them? Well, what's the same? between those two graphs? Yep, the same starting point. Which in both of these graphs, actually, we can call that the vertex as well. So I'm just going to throw in a little vocabulary. Cool. What else?
It's the same method for finding the vertex?
Yeah, same method for finding the vertex as well. You could talk about how the number inside with the x moves it over, the number outside moves it up and down, minus still goes right. All that stuff is the same. If we wanted to, we could even notice that there are even a few points that are the same. Notice there are 3 points that are exactly the same between these graphs. But notice it's only those points, it's not the curve in between them, it's just those 3 points happen to be the same. Okay, so if those are what's the same, what's different between the two graphs?
What's it called when you go up and over?
Rise over run.
Thinking like slope.
The slope, for the purple one, it's the same, so it's
Yep.
like 1 over 1. But then for the blue one, it changes each.
Yeah. The absolute value has a constant slope, and the quadratic, it doesn't actually have a constant slope. The slope is always changing as you go along there. All right, and now actually note on that. We talked when we did absolute value about how we could actually know what the slope was all along the sides. We cannot talk about slope when we deal with the quadratics because there is no constant slope. So we won't actually be able to use that wording for it. So slope is one thing that we can talk about as being different. What else is different? Well, kind of related to that, because there is no constant slope, we could talk about the shape being different. But by and large, they're very, very similar. And you're going to find that all the rules that you learned about for absolute value are actually going to be carrying over into the quadratic stuff as well. All right, so to practice now, I'd like you please to graph these 3 equations, each on a separate axis. Don't try to do them all on the same, otherwise it just looks too convoluted and messed up. So do each of these on a separate set of axes, and then we'll take a look and see what they all end up looking like. All right, to start checking these, here is the first of those graphs, y equals negative x squared. Notice what the negative did. Just like with absolute value, it reflected it across the x-axis. Basically flipped it upside down. So our vertex didn't move in this case, but our points are going down instead of going up. And so then the question comes up sometimes, okay, but isn't a negative squared always going to give us a positive? Yes, and that would be the case if we were given that, with parentheses around the negative x. But when we say negative x squared without those parentheses, what it's saying is do x squared and then apply the negative to it after that. Okay, here's our second one for you to check. X minus 3 squared. Now, with this particular one, I'm just going to take it as an opportunity to mention one tiny little detailing thing that sometimes comes up. It's one of those tangential ideas when it comes to graphing these. You notice how it's symmetrical on both sides? We'll often talk about it having an axis of symmetry. The axis of symmetry is basically that line that goes through the middle of it, where it's symmetrical on the left side and on the right side. In other words, you can mirror it over that line. If you're ever asked to give the axis of symmetry, what you're going to do is you're going to give the equation of that line. So for instance, if I asked you what the axis of symmetry was for this particular problem, you would say that the axis of symmetry is x equals 3. And yes, we'd have to have the x equals, because by writing it as x equals 3, it makes it the equation of a vertical line. And it's actually the line that we're giving here, not just the one number. And then the other graph there, x squared plus 5. Again, notice the plus 5, it moves it all up 5. All right, so now that you've done them all separately, here let's put them all together into a single equation. And I'd like you to please graph that equation. please describe the transformations and then tell me what the range is going to be for this graph. As you go and graph this, notice there are 3 different transformations being applied. They're the same 3 that we just did separately. So that minus out front, it should be reflecting across the x-axis. The minus 3, it's inside with the x, so it's moving it left and right. Minus moves right, so that one's going to go right 3. And the plus 5, it's going to be moving it up 5, because that 5 is hanging on the end. And so then this is what you should be looking at for what the graph comes out looking like, and what the transformations are, and how we'd write those out. So you get this down, you make sure everything's correct, and then we need to get the range. The range, remember, is that description of the y values that are included in this graph. So this one goes up to 5 and includes all the y values below it. So our range here is going to be that y is less than or equal to 5. Hopefully, after going through all this, if you could graph absolute value, hopefully you see that now you can graph a quadratic, because it's all following the same rules, just a different shape.